Hey, y'all, it's Dr. Know-It-All. I am with Dr. Scott Walter. Again, we are going to do an addendum, I guess, for the hand episode. So, of course, we'll put a link to that probably up here and also at the end of the video. But you wanted to talk about the thumb this evening. So let's talk about Optimus's thumb. You have some new insights.
Well, the insights come via Tesla because they evidently put something out there. I don't know if they tweeted it or where it is, but Sawyer Merritt said, oh, Tesla just released this video of the hand, and I took a look at it, and so it's kind of courtesy of him. And so I'm just going to share and give us a little recollection of what was going on in the hand design, and then look at the thumb, because we were kind of trying to figure out what that weird looking hinge mechanism was all about.
Right. It looks like a door hinge, just a standard door hinge. It looks like you could buy it at the hardware store. So I haven't seen this. I haven't seen this video yet. So definitely show me this video.
Oh, okay. Okay. Yeah. So I assume the screen sharing is working correctly here.
Yes, I can see it. I don't know how chunky it'll be in terms of like playback, but we'll see.
Oh, okay. So we see the biologically inspired design. This is one of the slides from AI Day.
Yeah, yeah.
Where we get a close up here, and we can sort of see that everything is tendon driven. We notice the finger lengths are all the same. They're just offset a little bit to give the impression of the shape of a hand. And they have these different drive units, these servo drive units along here, which are pulling on here. Basically, this fishing line with a little bit of spool on the end. And we already looked at it in one of the other videos of what this design looks like. It's basically this. So the finger drive is a clutch-free drive, and it has like non-back drivable, etc.
Which basically, again, for people who didn't watch that other one, it means if you curl your finger, it'll stay there without applying energy. So you don't have to provide energy.
It should. It should do that. And now they have actually two of them arranged along here for the thumb.
Okay.
And the top one here seems to drive this spool right here.
Right.
And this one is connected to something here. And if you notice, both of them are along the same axis. So I just want to point this out, because when we go over to the video right now, it's going to be interesting. It's a pretty short video.
Okay.
And let's see where to go. Oh, there it is. Okay. So we're going to bring it up. So it's like a 15-second video. And I'm going to start in a second. But the first thing I want us to notice, we can already see how the power is getting there. We can see, and now the light keeps on changing. They make it very confusing. I think there is definitely a black wire. There is a red wire. And I think there's a white or a green wire. So it's going to be one of those episodes like the green wire. I don't know which wire. It keeps changing color.
It'll be like the what was that dress that people were like convinced was gold or green? Oh, this is the start of the Tesla AI Day. It sort of counted down and then it did this. But but I don't think it did it from the inside before. Oh no, this is longer. Okay. Yeah.
So it's the first public release, I think, of this. Okay, so what I'm going to do is I'm going to go through here. The one thing we can notice is that there are springs right here at each knuckle. And the idea of those springs is to force it to open up when there's no tension on the gables. So that's just enough to be able to open it up. And I'm going to scroll through this a little bit till we get to one of the other gestures that it's going to be doing here. We can see the thumb opening up, and we can definitely see the springs pretty well. Not too much is being revealed there. And then now this is where it starts to get interesting.
Yeah. And this is also new, because I think all of the other pictures have been from the backside of the hand, not the palm.
Yes. So we're now going to see it. The lighting is still hiding a lot of things. We can begin to see right up here. There's a tendon. You can see the tendon coming in here.
Yeah,
and over there for sure. That is definitely coming in there.
And also we can see that the palm now has like kind of a soft, probably rubbery materials for gripping.
Yes, definitely it does. And now the lighting is going to change, that we can begin to see on the thumb right there as it pops around a little bit.
Okay.
Here is the tendon that goes through the thumb.
Oh, yeah. Okay.
And this wraps right around the spool right here. Now, it's not doing anything. It's actually in a relaxed position. So the springs are the reason why the thumb is completely extended out like that.
Right.
So the tendon is actually doing nothing. And what we're seeing is rotation about this axis being done by the second servo down here.
Right.
So it's moving it along. And what I want you to see is that tendon is getting unwrapped.
Yeah.
It's unwrapping. Look right around there. It's unwrapping off the spool, which means the tension on the thumb is getting less and less and less.
Right.
which means
Right.
it's really just the torsion springs at both those knuckles that are keeping that thumb out. So that's the reason why it's there. And this is what usually happens is you have coupling between different joints. When you try to do this, you move one joint and the other one will just move.
Right.
There's not much you can do about it, except that you have to counter rotate. Now it's going to get a bit more interesting here as we come in, it finally locks up, and now it's going to close the thumb. And I would love to have seen that move with the thumb closed first, not open. Because what I want you to notice right now is, I'm going to back this up. When this thumb starts to close, do you notice that that hinge kind of pops a little bit there?
It sure does.
Moving. There's a little bit of movement in there because now there's a lot of tension on that, and it's inducing a torque about the same hinge.
Right.
And that's probably being felt a little bit by that drive. Now, I know they're supposed to be non-back drivable, but I wonder if there's some slop or something else in there that's kind of causing that little bit of a wiggle there.
Right. Well, I mean, if you think about it, the tendon that was in there was completely relaxed, and as
it was relaxed, and now it's under,
as it tightens up, it's going to just change the tolerance of that other the whole joint.
It's under tension, and it's going to kind of cause that to move. And I think if you look at it, you'll see it kind of shimmies backwards and forwards. So if again, I'm not exactly sure where Tesla put this. Sawyer Merritt found it. So all I know is I just went to his tweet and opened it up, and whoop, there it is. And you know, this is the rest of it, which we've all sort of seen this before. But I thought it was rather interesting. This is the first time we are seeing both motions in the thumb and how it's being accomplished, and that there is no tendon doing this one. And that's what everyone's wondering. It's like, oh, are there two tendons on there? No, there's only one. And you can see the difficulty of having tendons mixed in with other drives, especially if you were to run this tendon all the way through the wrist and have it up in the forearm. You would make it even more complicated. And then if you're driving it through your shoulder all the way down to your torso, you know, there's even more of that interplay and coupling that's going on. Now, if we were to model this the normal way, writing our own little heuristics to model the kinematics for this and some of the backlash and everything else that you'd be having, and looking at the spring constants you're going to have in your in the tendon, it'd be a rather complicated model to put together to be able to deal with that nuance, to be able to compensate. Because what you'd think you would need to do is like, oh, when that starts to move, I need to maybe move that drive a little bit to compensate, especially if there's a lot of coupling there. And that'd be rather difficult to model. But with machine learning, it'll probably figure that out after a while. It'll kind of notice, wait a minute, I really have my thumb over here. It's moving a little bit out of place here. What should I do? And then it will probably already do that compensation. It's also very difficult to do this heuristically because every one of these robots will not be identical. I mean, it's really hard to make two identical springs have the same spring constant. You know, it's the same thing like with resistors and electronics, you know. If you look on there, what they say, some of those stripes that are actually on there are like the plus or minus. So just because it says it's 10,000 ohms does not mean it's 10,000 ohms plus or minus a certain variance, and it varies with temperature and everything else. So it is very hard to have two identical versions and then assume that, okay, the robot's going to do it. So the robot's going to have some sort of calibration procedure. And as a matter of fact, industrial robots do that already. Supposedly they're identical. So like one of the robots goes down the line, you should just be able to scurry in there, like unbolt it from its pedestal, come with a backlift, pull it away, drop the next identical one, put it in there, load the program and run it. And you do that and you find out, whoa, wait a minute, it's missing all its locations because they're not really identical. Now it's much better because all the robots have what they call the signature file. They go through a routine where they go and actually figure out what are all the construction errors that are in there. Because even though the hardware is very stiff and rigid and they try to manufacture to extreme tolerances, by the time you put it together, you get all these stack up errors and simple things like an encoder zero offset that's not quite where you think it is. And so you need to capture that information. And then once you have that, you can make them identical. So the same thing is going to happen here. It's going to have probably some sort of procedure it goes through where maybe it's like, oh, just go ahead and like touch your fingers. And, you know, oh, I'm a little bit off there. Oh, okay. What do I have to do to compensate? And so it'll probably do something like that. Almost the same way like a pianist, you know, when they warming up, they're going through and making sure, oh, okay, I know where my fingers are today. I bet there'll be some similar routines like that that you would go through to make sure that you're in calibration.
That means to a large extent. So I guess the question is how what is it using to sense that? Because you can use vision, and of course you could be like, okay, now we're connected and we're making a okay sign. Is there a way with all of the sloppiness of these springs and the tendons to be able to use any other types of sensors like force sensors? Because how do you know your thumb is exactly this, curled up if you don't look at it?
It's going to be interesting to see how they do the force sensors and whether they have position sensors already built into the servos, which they may have some way of being able to count that.
Right.
And also,
but even so, like a servo, this isn't direct drive. This is through a tendon. So there's just going to be a lot of slop in there.
But on the spool, there's going to be a kind of a torque that's going to be on there, and you should be able to measure that probably through the current or other things. So using calculus and a few other things, you can probably infer what those forces are in many places. And then maybe there's something when you bring two fingers together and you try to see, okay, what's the force component like? Is it what I expect? But I would think you might have some sort of tactile sensors on there at some point, or it could just be vision. Like, oh, look at that! Oh, I'm off.
Yeah, because it could.
It's like that scene in RoboCop. Remember, he was like all out of calibration, and he's like kind of looking, and he's like shooting, and like, oh, I'm off 6 inches to the left. Calibrates and does it again. It might be a similar thing like that you can just use a camera, and you see, wow, I'm way off. Oh, now I'm on there. Right. So this is a debate that I've been seeing today in some of the Twitter threads. Everyone's wondering what kind of sensors are going to be in the fingers. And I wonder if, I don't think there's going to be any at first. They're probably going to see how far we can get away with just measuring probably the feedback from the motors itself and also the vision system and what it's able to see how far they can get without having to add more proprioception anywhere within the system.
Gotcha. So can you back this up a little bit? Because there is a moment when it tries to do the okay, but it actually doesn't do it properly.
When I back it up.
When the thumb and the forefinger are curled. So keep going back. Oh, wait, where is that? Oh, maybe it's further forward.
I think it's forward.
Yeah.
Here.
But it tries to make the okay sign, but it doesn't work properly. They don't actually sync up and touch each other. Yeah, here it is. So watch. It's like it gets down.
It's like not quite
right. So it's not quite there.
Well, you got to remember is that the problem they have here is they don't have individual control of each of these bones. So when they're doing the tension, they get whatever curl they get. And so when they're trying to close the thumb, it's moving here and there at the same time. And and we seem to have a little bit more nuance. We've got a bit more control to be able to do that.
Right.
And I would not be surprised if that's something that if they do enough iterations, enough practice, they might figure it out. Because it could be a trick that what's happening is that this finger is well, let me get my hand over here, right? This finger is closing too quickly. And then this one comes on top of it.
Yes.
But if I somehow get it out there to say, okay, stop there. And now this is going to stop my thumb. And then I can continue to give it pressure and then change my shape.
Right.
So there may be a few little tricks that it's going to learn to do that after a while.
Or, I mean, it's also possible they intended it to be like that instead of touching. But I think that if you back up,
they intended it. If you ask them, they intended it.
Of course it is. So if you back it up a little bit, you can actually see that the index finger definitely closes, and then the thumb closes around it. So they should be
able to control independently. That's what I'm saying is that what it might be is that they were too quick with the index finger and too slow with the thumb. And maybe if they got. And are they trying? Well, it's almost like they are trying to, you know what? Look at this.
I think they're striking
intentionally closing it down there.
Yeah.
They're probably closing the index finger too much. They could get it a bit higher, but they're using the impact of the index finger to cause that thumb to buckle.
Right.
Because it won't buckle otherwise.
Right.
And then what's happening, of course, is now you're exerting a lot of forces on the tip of the index finger, which is causing the index finger to buckle because they don't have any control there. And the only way they'd be able to maybe change that is they would have to make the spring constants a bit stiffer.
Yeah. Well, if you look at that, if you back it up just a couple of frames right before they both start to curl, and because you can see the index finger actually strikes the inside of the thumb, but
strikes it right there.
Just before it
causes it to collapse.
You can see how both of them are very straight still. So neither one is curled, and it's that impact that causes them both to curl.
Exactly. So the initial motion is that when you are putting the tension on there, all the torques are being felt down here at the base.
Yes. And you can see how straight.
It's only when the
finger
base
is very, very straight.
The base has to get locked. Once the base gets locked, something will happen. Now it will close. So the base is locked kind of allowing it to do it, but at the same time, it could be the collision with the thumb is having a little bit to do with it.
Right.
The thumb, I think, could go up higher. Oh yeah, you look at the thumb was up high. The thumb was up high. It strikes, and now the base of the thumb suddenly collapses and goes the opposite direction.
Yeah.
That then causes the tension. So that's they don't have the nuance. But I don't think they necessarily need it for the application that they're looking at.
Exactly. Again, I think going back to what you had said before, as long as it can pick up a power tool, it's going to be able to do what it needs to. I version 1.0.
Yeah, I looked at Osmo again today, and I noticed that they have all of the knuckles. They did not decide to reduce the number of bones in their fingers. Right. Tesla has decided to go ahead and do that. And, you know, the thing I pointed out is I sort of asked the question, you know, when was the last time a factory floor position had, you know, doing backflips in the job description?
Right.
It's not part of the job description for just about anything. I mean, name any job where you need to do that. And then snarkily, I said, well, okay, sometimes figuratively, you're expected to do backflips. You know,
well, I guess if you're trying to get a job with Cirque
but literally, no, you're not expected to do that. So they are really trying to find the minimum viable product that is going to be able to accomplish exactly what they want, and then they can start getting them out quickly.
Yes.
So, yeah, I keep on hearing everyone's like, oh, but Atlas this and Atlas that, and I'm like, forget the 5. You know, remember the 5 principles. Right. Remember the 5 principles. We forgot to talk about that a little bit.
Yeah.
That's what the whole design process is being done. You know, first, you know, make sure the requirements are not so dumb. Yeah. And adding the extra bones in the hand probably is like a dumb requirement. Right. Making sure the hand is exactly identical to a human hand is dumb. Yes. All you need to have is to make sure that you have an opposing thumb. And that will work for many, many applications. And again, we are not trying to change watch batteries. We're not trying to have that kind of delicacy. Right. But in the factory setting, many of the things that they're doing, they can do with very coarse kind of positioning and still get the job done.
So a lot of people also have been talking about the fact that the head is not swivelable and saying that is a significant problem. Well, you too. But I sort of feel like the fact, and again, I'm going to go with the 3 cameras because I'm pretty sure that that's what they've got from the evidence. That first camera is probably 140-degree angle of view. So that means not just side to side, but up and down. So he can see quite a bit. Is
it up and down, or is it a little bit wider?
It may be slightly wider screen. Again, I don't know. It looks like that, but I don't know what the actual raw camera input is. They also did not stitch the images together for us. They only showed us the individual images in the pictures. So, but regardless, it has a lot of, it can see a lot. And especially when you add the 2 side cameras. So yeah, it definitely, you can see it bend over when it has to look down and pick things up. But, you know, at the beginning of again, what's the minimal viable product? Yeah, it would be great to have a fully rotatable head. But for version 1.0, that's a lot of extra complexity, a lot of energy. And what do you get out of it? In some ways, it's actually better not to, because they have, just like an automobile, they have a stable platform for the cameras. Because just imagine if the actuators and stuff in the head were causing it to jiggle around and stuff, it becomes much more difficult to know exactly where you are in space. Yes. So, you know,
I agree with that. And what was interesting is that if you look at version 0.0, which was the concept, it was in there. And then when they go to Bumble C, they immediately took it out. It's like, wow, that was like a really quick, you know, someone said, well, wait a minute, you know, do we really need it? Will the field of view work? And my concern is, you know, what that field of view is. And I was noticing, watching the videos and their view, what Bumble C was seeing is the object was pretty much in the center of view. It wasn't like it was down low. And I'm wondering if they really do want to keep it in there, or if they're doing something with the camera. I mean, not necessarily moving it, but maybe digitally kind of tilting it down to be able to keep it in there to say, this is our focus that we want to have. Or something else is going on. But it did seem like it was leaning in, and I was beginning to think, but it's really leaning in a lot there. And, you know, and it was because it seemed like it really wanted to get the head over there. So again, it's typical of Tesla that they solve a lot of hardware problems through software, and they realize, wait a minute, we already have enough agility in the hip and
Right.
everything else. Let's just go with that and test it out. And then we'll find out down the road whether they decide they need to add 1 or 2 axes there, or they'll do something with the eyes. I mean, there's so many solutions there. I don't know which one they're going to come up with, but
well, honestly,
if
if they needed to, they could always add one in the chest also. You know, they could just pop another one.
They could, or one in the chin. I don't know.
Or one in the chin.
Maybe there's one there just to extend the field of view down there, or maybe that those Samsung cameras are so good that they get such a big field of view. It's like, doesn't matter, you know, we can still be up here and get a pretty good view. Yeah. So
because there's a lot of pixels in there. So
the
what was I thinking about? Just thinking about the way that it actually moved around and everything, it has to be able to see the ground relatively closely in front of it as it walks, which means that it needs to be able to keep its head upright, because it you know, it's not a good sign if you want to walk looking at your feet. So it has to be able
it's
to,
like a nerd, you know, just looking at the toes the whole time.
So, you know, it has to be able to at least have a field of view where it can see down to maybe a foot or 2 in front of it where its feet are, because it doesn't want to run into anything. But that will be a limiting thing. But the other thing is, you remember, it doesn't care what's above it. So you could take
it would be angled down.
You could take that camera and just angle it down so that you're only getting a horizon that's a little ways above its head. But most of
we're assuming that cameras like this, amount like that, probably already down a little bit. And again, so it seems like there's a pillar on each side, and there's only a fisheye in the front. And from that, somehow they're able to get enough stereo.
I think what they're doing is they're cheating that using that tracking option. So that's what I had. If you don't know what I'm talking about, watch the video I did this morning. But they have this high frequency data. Actually, I guess it was yesterday morning. But anyway, they have this high frequency data that they're tracking. So everywhere that there's like a computer monitor that goes into the white wall behind it, there's like little tracking dots.
And so, all those dots.
And so as it moves through that space, it's able to just use basic parallax. I mean, that's
okay. So it's basically building it up, so it's more of a record of what the 3D world would be, as rather than an instantaneous stereoscopic view.
So, and again, it has the other views, so it's probably able to stitch some things together and use stereoscopic.
But the question is how much overlap, because they're really pointing that way. I'm like, wow.
Well, if you look at
just a little bit of overlap, I wonder how you really get a good stereo from that.
Let's see if I can bring this up real quick. I've got to find it, but I had some a couple of pictures will do an awful lot of good. All right, give me 1 sec. Keep talking.
And once again, I promise, John.
Here we go.
Under 15 minutes.
No. I got this. We're good. This is actually worth bringing up, though. So let me share this one, because I think this will help people to understand. Okay, can you see that?
Yes.
Okay, so look at the top. You've got left pillar camera, fisheye, right pillar camera, and look at how much of this human. He's highlighted in green here, but he's overlapped a lot between the two. And then this guy has a huge amount of overlap between the two. So, and of course, up here in the original images. So that gives you a pretty reasonable amount. Now, it doesn't give you anything directly.
That's the problem, is dead center. You don't get the stereo. You lose it right where you want it.
So I think that they must be using something else, because there's, you know, when you look at the other images, there's this panoptic segmentation that's going on where you can definitely tell that it's doing something much more like down here. This occupancy network is probably a couple of centimeters cube, like a cube that's a couple centimeters big, right? So it's not very accurate. So that would be, you wouldn't be able to use that. But if we go to,
there's probably enough information, because one way of getting a stereo is you don't have to have 2 cameras. That's all about time lapse. Like you take a picture here, you take a picture there, and you put them together. And from the human standpoint, we need the stereo input, because that's just the way our brains work in order to get the 3D map. And someone probably realized, like, it doesn't really need stereo, does it? I mean, all it needs is a 3D world in its head that it understands. And whether we stitch it together instantaneously through this trick of stereoscopy, or just making a 3D world like that, it probably doesn't matter. So my feeling is that, again, they're like, okay, we don't necessarily have to do it the same way we do it with people. Or humans.
Well, again, it's that minimum viable product. But here you can see, so again, for people who haven't watched the other videos, you've got green for human beings, but you can see how that's very, very tightly, like, the outline of those people is very tight. And then you've got red for the plants, which is the target. You've got this blue color for the watering pot. You've got the teal color for his hand, and the purple for the ground, and the white for the background. So that's very, very tightly controlled. That's not at that, kind of multiple centimeter level of voxels. So very different.
And in that image, you can see the hinge mechanism really well.
Yeah, right here.
Thumb. So you can kind of point that out a little bit. You can see sort of where the two hinges are, that it pivots around.
Right.
Yeah.
Well, and also look how useful this is. That OK sign that it made, that we were looking at right here, you can see how that is very useful, because what it does is it uses the thumb as a curling mechanism to force the
other one in.
Close. Yeah.
It may be.
Yeah.
So it may be that they don't really want to do perfect hand gestures because it's not necessary.
Right. Or actually could be
the jobs they're doing, it's good enough. Yeah.
Yeah. It could be actually counterproductive, honestly, in a way. So
yeah.
And let me bring this one up finally, just to make sure that we've got everybody. All right, let me stop and bring up this guy. One more image, just so we're complete with this. So now this is the high frequency data that I was talking about. So what I mean by high frequency is just very rapid changes in color or luminosity in an image. So you can see what they're looking at is the places where the white, planter box meets up with the darker plants, or with the where you've got the edge of the monitor connects. But this, you'd get parallax as you move through this. The farther away dots are going to move very little, and the close-up dots will move a lot.
The way you can think about that is that this is basically celestial navigation. This is an old trick of photogrammetry.
Yes,
that you go through and you identify those things, and they become these stars, and you see them in different images. And all you're trying to figure out is, what are there a couple of stars that overlap? And once you realize that, like, I'm over here and I can see Orion's belt, and somewhere else you see Orion's belt, you now can kind of put it together and kind of know where you are in the world, even if you both don't see the same thing. Now, Orion's belt might actually be a really bad example, because it's the randomness of the stars that makes things work out.
Right.
Because you've got this least squares fit that's going through there, trying to find out what the stars are. And if you actually have a pattern, which is a perfect pattern, you don't know where you are. You're completely lost, because everything looks the same. So that was really surprising photogrammetry when they were putting the stickers, like on a 737 or 747, you just put these stickers all over the plane. And with one camera, you just keep on going around taking pictures, and you're just looking at the overlaps between the frames to say, oh, that's where this is where that is.
Right.
And I was surprised. They're like, don't put them in a straight line. Just flap them wherever you want. You're kidding me. You don't have any, no, we just want them random. Just keep them random.
Right. But that's basically it, because you've got random points that have all sorts of depth information. Now, the one critical element of this is that it's going to have to move through the space for it to be useful. But I mean, that's what the robot does. And of course it can remember this. I mean, so this is just, honestly, this isn't machine learning or anything. This is actually just an old trick.
Oh, that's old. That's really old school.
This is, like you said, it's parallax. It's what sailors used to use to figure out where they were on the ocean. They just look up at the stars and they'd figure out. So, this is just basic math that they're doing here. So nothing
really
super complicated.
Squares. It's numerical algorithms have been around a long time that they can run really fast. So all they have to do is identify where those corners are.
Right.
That that's sort of the new thing, that they have to go and filter the data and identify the corners on those monitors and make sure that's always there.
Exactly. So so I mean, what you think about is that that's really, really fast to calculate, and that cheats and gives you your GPS. Because what they're missing from full self-driving is, when you do full self-driving, you've got these lovely GPS satellites that are telling you where you are. So this is what it's doing for that, and then it uses the 3D occupancy network to block out areas, like general areas, don't hit the people, things like that. And then it has this segmentation scene, again, all this stuff from full self-driving, where it blocks out and says, this is the watering can, this is the plant, this is the planter, that's a human being over there. And you can, just block out all of that stuff. And so each of these things can operate it really probably very efficiently.
They're very fast. They can have their own separate thread, and they'd be able to keep up with it. And you don't need any other tracking devices or anything else. And again, it's not moving at 60 miles per hour.
Right.
It's moving slow enough through the environment. And if something happens that it's not sure where it is, well, it'll just stop until it calibrates and is able to pick up the data.
Exactly. Yeah, I was looking at Bumble C, and like his neck stalk is literally like an extruded aluminum I-beam or so. It's like just something that somebody just went into the shop and cut a couple of pieces and stuck it on there.
I know, John, you know, everyone thinks like, oh, you know, each one of those robots cost $1 million. And it's like, $1 million in engineering hours.
Yes, it's mostly the
actual material costs.
Right.
It's probably $20,000 or less if you think about it.
Oh, sure. And I mean, you could see like a lot. I actually liked Bumble C better because he had lights all over him that was flashing. It was, very old school robot. But, you know, those are clearly just, you know, Ethernet things and stuff that are flashing that are telling you the Ethernet's working as a communication between. So real basic stuff that they're working on in that original model. But I think what this did was this probably allowed them, because I have a feeling they probably had a Bumble C head. And then they had a version 2 of that head and a version 3 of that head where they were like, okay, can we get rid of these cameras? Can we do this to it? Can we do that to it? And then they're like, oh, this is the one that actually works. And it's the minimum amount of stuff we need. So yeah.
Constantly removing parts, trying to find out where they can economize things. And that's what I was wondering with the hand. We saw the wires that were going in there.
Right.
Do you think there's some other hidden wires we're not seeing, which are the communication to the servos, or do you think they can actually do it over those 3 wires?
Oh, wow.
Because 2 of them might be power and one of them is sort of for communication.
Could be. Yeah, I don't know.
You have a lot of smarts in the servos to be able to look at the data packets that might be coming to them to say, oh, this is your command. So they may have something set up like that.
So in that case, would it just be serial as opposed to parallel? So it would just be a serial port, and it's basically firing off pinky, do this, you know, it's just going.
And they just cycle through and just kind of wait for their data packet to know what they're doing. And depending upon how fast it has to move, that might be good enough. So I was wondering if they're snaking any other cables behind there that we're not seeing.
Right. The other thing that those, what are we looking at? What do you think voltage would be for those wires?
I think it said somewhere. I think it said 52 volts.
Yeah. So that's what I mean. It's like a medium voltage. So it's using a, you know, it can get away with pretty small wires. But I think you're right. I think it was 52 volts.
Which is interesting because I thought that the Cybertruck is going to be 48.
Right.
So I wasn't surprised that they had different voltage. Somewhere it said in here, but you have to look at it when they got to the servo section. There was some information about that.
Yes.
Yeah, I don't have it available right there, but it seems to be in my mind that it was more than 48 volts. I sort of remember that.
Right. I think 52 is right. And then it was 28 actuators, but I believe half of that, like 12 of them were in the hands, right? So there was
yes.
5, 6, 12, yeah. So 12 between
28, exactly.
Right.
Exactly.
Yeah.
2 in the torso, 6 in the leg, per leg, 7 per arm, and then 6 per hand.
Right. Yeah. So quite a bit. I mean, obviously the focus is on the hand, but they get away with a lot by cutting out a lot of the head mobility. And also just remember this little guy right here, that would be another 8 that they would have to have just to include that extra little ability.
Yes.
So that's great that they're like, this is, again, as long as it can pick up a power tool, doesn't have to change a watch battery, doesn't have to paint a painting, doesn't have to have that incredible dexterity that we humans have.
Yeah, not yet. And who knows, eventually they will.
Right.
I would not be surprised if long-term they find out a way to get rid of the tendons and do something else.
More like direct drives.
Initial guess was like that tiny little actuator.
Right.
And you know, I was kind of disappointed that I was really wrong, but I don't know. Maybe someone there is going to look at it and say, okay, I see what the idea is.
But I mean, it seems like that's something that they would do because it will reduce complexity. So probably they went after the low-hanging fruit first, which was the big actuators that they really needed to be custom built. So you could tell the one that was in the center of the torso or the hip, and then the one that would rotate it sideways, those two are beefy things. And so they needed to get those done. And so this was probably like, we can get away with this for now, but I would not be at all surprised if they were direct drive actuators in there eventually, because you'd have a lot more dexterity. And probably a lot
Yeah,
more understanding
eventually
of
long
where
term,
you
but for
were.
now, this was the easiest route to be able to do it.
Right. Yeah. So really fascinating. Wow. we got into a good deal of stuff on this. I think that's very cool.
Once again, we take a 15-second video and what do we turn it into more than 15 minutes. I told you 50 minutes,
right.
no more, probably less. I promise.
Well, I mean,
but it was your fault. You went completely off script here.
I'm just saying we have access to animations finally, as opposed to still frame. We made so much hay out of still frame images. Now that we actually can see them moving, it's like, oh my gosh.
Oh yeah, that's the problem.
A kid in a candy store.
More data there.
So yeah, but yeah. So I hope this is helpful for people. I think, maybe we're getting into the weeds too much for some people, but I think this is valuable, because what we're doing is kind of setting a baseline. And so now in 6 months or a year or whenever they give us, Optimus 2.0 or 1.5 or whatever he is, we'll be able to look at that again and say, oh, look what they did. They've made these changes and now it's simpler, or they left it the same. And apparently that worked, So
So I guess the baseline is what now? 30-minute video.
Yeah. Okay. Well, yeah, we got the baseline video. I was talking about baseline Optimus, but we also got our baseline video. So there we go. All right.
It's under an hour.
That's right. Exactly. People should be happy about that. At least we're focusing relatively much on what we're doing. All right. Any final comments? Otherwise, we can bid everyone a fond adieu. So,
well,
all right.
Welcome home.
Thank you. It's nice to be back again.
See you in your studio again.
Did you see? I've got my AI Day 2 right. Oh gosh, I have to do it backwards. Right there.
Unfortunately, I have only one ribbon, and hopefully someday I'll get another one.
There we go.
Quite the collection of ribbons.
Starting my collection back there to hang on my Tesla tequila bottle. So, all right. Thank you to everybody so much, and especially to you for spending the evening with me. I guess this will be tomorrow morning when it comes out. But anyway, we'll see you later, and thank you so much.
Yep.
Bye-bye.
Cheers. Bye.